Welcome to another deep dive. Today, we're going to be looking at the Kochen-Specker Theorem.
Oh, fun.
Yeah, it's going to be a really interesting one, I think, and might make our listeners' brains hurt a little bit.
Little bit.
Well, maybe a lot. I know I struggled a bit getting my head around this one, but that's why you're here, to walk us through it.
Well, I'll certainly do my best.
So, the Kochen-Specker Theorem. It's this idea in quantum mechanics, and I know physics can be a bit of a headache sometimes, but stick with us. It's worth it.
It really is. It has some profound implications.
Yeah, and I think it's especially interesting for philosophers, right? Because it really gets into some fundamental questions about reality.
Oh, absolutely.
So, to get started, let's imagine for a second that all the weirdness of quantum mechanics, the randomness, the uncertainty, all that jazz, could actually be explained by something simpler. Like maybe there are these hidden variables, these things we just haven't figured out how to measure yet.
Right, right.
And these hidden variables are kind of pulling the strings behind the scenes, so to speak.
Yeah, like a secret code we haven't cracked yet.
Exactly. It's tempting to think that way, isn't it?
Yeah.
Like maybe the universe is just a giant clockwork mechanism, and if we knew all the gears and cogs, we could predict everything.
It's a very appealing idea, and it's where the whole concept of hidden variables in quantum mechanics comes from.
So how would these hidden variables actually work?
Well, imagine that there are these hidden factors that determine the outcome of every single quantum experiment.
Okay.
It's a bit like saying that a coin toss isn't really random. If we knew everything about the flip, the force, the angle, the air resistance, all those tiny little details, we could predict whether it would land on heads or tails every time.
Oh, I see. So these hidden variables in quantum mechanics are like those missing details, the things we haven't grasped yet.
Precisely.
So basically, these hidden variable theories are saying quantum mechanics isn't truly random. It just looks that way because we're missing some information.
Right. You got it. And that brings us to some crucial assumptions that underpin these hidden variable theories.
Okay, like what?
Well, one of the big ones is called value definiteness, or VD.
VD, okay.
Yeah. And this one is right up the philosopher's alley.
Sounds intriguing.
So value definiteness basically says that all those things we measure in quantum mechanics, all those observables, as they're called, actually have definite values at all times, even if we don't know what those values are.
So it's like saying, even if we're not looking at a particle, it still has a definite spin, momentum, position, all that stuff. Those properties are already there, whether we measure them or not.
That's it, exactly.
Interesting. So that kind of leans toward the realist camp in philosophy, right?
Yeah.
The idea that there's an objective reality out there, independent of our observation.
Right, right. Value definiteness definitely has some realist vibes.
So we've got these potential hidden variables running the show, and value definiteness says they have specific values, even when we're not looking. What's the other big assumption?
The other one is called non-contextuality, or NC for short.
Non-contextuality.
And it basically takes value definiteness a step further. So non-contextuality says that the value of a property, let's say the spin of a particle, isn't affected by how we decide to measure it.
I think I see what you mean.
Like, if a particle has a definite spin direction, that direction is the same whether we measure it along the x-axis, the y-axis, or the z-axis.
Oh, it's not like the way we measure something influences the value we get.
Exactly. It's a very straightforward, independent kind of property according to non-contextuality.
Got it. So both value definiteness and non-contextuality basically assume that there's this solid objective reality underlying all the weirdness of quantum mechanics.
You could say that, yeah.
Like, we just need to find the right tools to unveil it, and then everything will make perfect sense. Seems pretty reasonable, doesn't it?
It does, doesn't it? And for a long time, a lot of physicists really hoped that this was the case.
What?
But there's a twist. And this is where the Kochen-Specker Theorem comes in to shake things up.
Uh-oh. Sounds ominous.
It kind of is. Because what the theorem shows is that these seemingly intuitive assumptions, value definiteness and non-contextuality, when you combine them with the basic rules of quantum measurement, they lead to a contradiction.
Wait a minute. Are you saying that hidden variables with those assumptions just can't work?
That's exactly what the Kochen-Specker Theorem implies.
I'm all ears. Tell me more about this theorem. How does it show that?
Well, it's a bit like a logic puzzle where the rules of the game clash with the assumptions you're making.
Okay, I like puzzles.
So the theorem uses a set of carefully chosen properties that we can measure in quantum mechanics. Things like the spin of a particle.
Right, those observables we were talking about.
Exactly. And it shows that it's impossible to assign definite values to all these observables beforehand in a way that satisfies the basic rules of how quantum measurements work.
Okay, hold on. You're losing me a bit. What are these basic rules of quantum measurements?
Right, sorry, let's get a bit more specific. Let's say we're measuring the spin of an electron. Now, there are some pretty straightforward rules that govern these kinds of measurements. For example, there's something called the sum rule.
Some rule.
Yeah, it basically says that if we measure the spin along, say, the x-axis, and then we measure it along the a-axis, and then we measure the total spin, well, this total spin value should be equal to the sum of those two individual measurements.
Okay, that seems logical enough.
Right. And there's a similar rule for multiplication called the product rule.
So if we measure one thing and then another, those measurements should add up to the total in a consistent way.
Exactly. These rules are pretty basic, almost common sense.
But that's where the Kochen-Specker theorem comes in and says, nope,
Pretty much. What it does is it constructs a whole web of these spin measurements.
a web.
Yeah, you can think of it that way. And what the theorem shows is that there's no way to assign those nice, definite values to each spin measurement beforehand in a way that satisfies both the sum rule and the product rule. You always run into contradictions.
So it's like trying to fit square pegs into round holes. The rules of the game just don't allow for those pre-existing values to work out consistently.
That's a great way to put it.
Wow. So the Kochen-Specker theorem is basically telling us that something's got to give.
It really is.
Either our assumptions about hidden variables, specifically value definiteness and non-contextuality, are wrong, or
we need to rethink our understanding of quantum mechanics itself.
this is blowing my mind. So what are the alternatives?
Well, that's what we'll dig into next. There are a few ways physicists and philosophers have tried to escape this conundrum.
I can't wait to hear more.
It gets really wild.
Yeah.
It really is a head-scratcher, isn't it? You think you've got this neat picture of reality, and then the Kochen-Specker theorem comes along and says, hold on a minute, not so fast.
Uh-huh. Yeah, it definitely throws a wrench in things.
Mhm.
So where do we go from here? What are the options when those comfy hidden variable assumptions go out the window?
Well, there are a few escape routes, so to speak. One way to deal with this is to say, maybe value definiteness is the problem.
Value definiteness.
Yeah.
Okay.
Maybe some of those quantum observables, those properties we're trying to measure, they just don't have definite values until they're actually measured.
Wait, so you're saying it's not just that we don't know the values until we measure them, but that they literally don't exist until the measurement happens?
That's one way to think about it, yeah. It's a pretty radical idea, but it's one way to get around the Kochen-Specker paradox.
It's almost like the act of measuring forces the quantum system to choose a value, right?
Yeah, kind of. It's like those properties are in this fuzzy, undefined state until we interact with them.
That's wild. Are there any theories that actually try to explain how this value indefiniteness would work?
Oh, absolutely. There are these things called modal interpretations of quantum mechanics.
Modal interpretations.
Yeah, and they explore this idea that systems exist in a kind of blurry potential state until a measurement collapses them into something definite.
So instead of imagining a particle with a fixed set of properties, we think of it as having this range of possibilities, and the act of measuring sort of selects one option from the menu.
You got it. It's a shift from thinking about fixed properties to thinking about potentialities.
Okay, I think I'm starting to get a handle on how ditching value definiteness might solve the problem. But what about the other option? What was it called again? Non-something.
Non-contextuality.
Right, non-contextuality. What if we question that assumption? What would a contextual interpretation of quantum mechanics look like?
Now that's where things get really interesting, especially for philosophers.
Play it on me.
So contextuality basically throws the idea of simple independent properties out the window. It suggests that the value of a property might actually depend on the entire context of the experiment.
So it's not just about the particle itself, it's about how we're measuring it, what other measurements are going on, the whole shebang.
Exactly. It's a much more holistic kind of picture, where you can't just isolate a property and say it has this value regardless of everything else.
I'm trying to wrap my head around that. So it's like saying the meaning of a word depends on the sentence it's in, the context of the conversation.
That's a great analogy.
But if everything is so context dependent, does that mean there's no objective reality at all? Does everything become subjective and relative?
That's a really good question. Contextual interpretations do suggest that properties are relative to the context, but that doesn't necessarily mean there's no underlying reality at all.
So maybe it's not about saying there's no objective reality, but rather that this reality is much more interconnected and interdependent than we tend to think.
Exactly. The Kochen-Specker theorem kind of forces us to rethink what reality could mean.
It's definitely a mind bender. Okay, so we've got these two main paths. Either ditch value definiteness or embrace contextuality. But how do we actually test these ideas? Can we do experiments to figure out which one is more likely?
Well, that's the tricky part, isn't it? Testing these ideas experimentally is a real challenge. You see, the Kochen-Specker theorem, it deals with these hypothetical hidden variables,
Right.
which by their very nature are hidden. So how do you design an experiment to test something you can't even directly observe?
Yeah, it's like trying to catch a shadow.
Yeah.
So are we just stuck with these theoretical ideas, or is there any way to get some experimental clues?
Well, physicists are a clever bunch, and they've come up with some ingenious workarounds. Instead of trying to directly observe the hidden variables themselves,
Right.
they focus on the consequences of those hidden variables. Like,
Right.
what kind of effects would those hidden variables have on the things we can measure?
I see. So we look for the footprints, not the monster itself.
Exactly. For example, if non-contextuality were true, we'd expect to see certain patterns in the results of our measurements, specific statistical correlations.
Okay.
And if those correlations aren't there, if the patterns are broken, well, that would be a pretty strong hint that non-contextuality isn't holding up.
So we're not looking for a smoking gun, but rather for subtle anomalies that suggest something deeper is going on.
That's a great way to put it. And actually, there have been some really intriguing experiments, particularly those involving entangled particles.
Entanglement. Now we're getting into the really weird stuff.
Yes. Entanglement, that spooky action at a distance that Einstein wasn't too fond of. But it turns out that entanglement provides a way to probe these ideas about contextuality without needing to directly measure those hidden variables.
Okay, now you've piqued my curiosity. How does entanglement connect to all of this? It seems like we've jumped to a whole different branch of quantum weirdness.
Well, the connection is subtle, but it's there. Entanglement basically allows us to test certain assumptions about the nature of reality without needing to directly observe the things that might be causing those assumptions to break down. It's like we're using entanglement as a proxy to investigate those hidden variables.
So we're kind of sneaking up on the problem from a different angle.
You could say that, yeah. And the results of these entanglement experiments, particularly those that involve testing something called Bell inequalities, they strongly suggest that the quantum world doesn't play by the same rules as the classical world we're used to.
Bell inequalities, those ring a bell.
They're named after John Bell, a physicist who came up with these clever ways to test the foundations of quantum mechanics. And what's fascinating is that these Bell inequalities, they get violated in experiments.
Violated.
Yeah, the experimental results don't match up with what we'd expect if the world were purely classical, if those hidden variables were behaving nicely according to our assumptions.
So it's like the universe is giving us a wink and saying, nope, not that simple.
Haha, exactly. And these violations of Bell inequalities, they provide some of the strongest evidence we have that the quantum world is fundamentally contextual.
Wow, that's pretty mind-blowing. So by studying entanglement, we're getting a glimpse into the contextual nature of reality itself.
I think that's a fair way to put it. The Kochen-Specker theorem, along with all this experimental evidence, it really pushes us to expand our ideas about what reality could mean. It might be far more interconnected, far stranger than we ever imagined.
This has been a wild ride, exploring the Kochen-Specker theorem, diving into value definiteness, grappling with contextuality. It's definitely made me rethink some assumptions about how the world works.
It's a real humbling experience, isn't it? Realizing how much we still don't know about the universe.
Yeah, and it makes you realize that we're just scratching the surface. Any final thoughts for our listeners? Something to ponder as they navigate this strange and wonderful quantum landscape.
I think the biggest takeaway is to stay curious, to keep asking those big questions. The Kochen-Specker theorem, it's not just some abstract mathematical puzzle. It's a reminder that we're still on this incredible journey of discovery. And who knows what other mind-bending mysteries the universe has in store for us.
A reminder to embrace uncertainty and to keep exploring. Well, thank you so much for guiding us through this deep dive into the Kochen-Specker theorem and its implications. It's been an absolute pleasure. And to our listeners, thanks for joining us. Until next time.